All right, this is the section we started in class today. This is section 1.3 in the book. It's these three things: continuity and behavior, which includes limits. We talked about continuity in class, so I'm not going to talk about that in the video. We're going to start with end behavior and limits, and then talk about something called the intermediate value theorem, which sounds kind of intimidating, but it's really not. So, hey, wait, I said next page. There we go. Right, end behavior, that describes what the far left and right ends of any graph are doing. If you look at these two graphs, and I'm going to be kind of lenient at first, but eventually I'm going to be real particular about how you say this. But for now, if you look at my left end, our left end's going up, and the right end's going up. And so that's the end behavior. What's happening in the middle, even though it comes down and goes back up, the middle doesn't matter. I'm completely ignoring that part. I'm only looking at what happens on the far left and the far right. And in this case, both ends are going up. This one, some funny stuff going on in the middle, but if I look at the far left end, the left end's going down, far right end is going up. And you could have other combinations also. You could have a graph where both ends go down, like that, with some crazy stuff in the middle. Or you could have one that starts up high and ends up going down. So we have those four different options. And right now we're going to be dealing with end behavior of polynomials. Polynomials? There is some other stuff with end behavior with some crazy functions, but right now we're going to keep it kind of basic and do end behavior of polynomials. So we could say left end goes up, right end goes up, left end goes down, right end goes up, both ends go down, something like that. That's the end behavior. But I do want you to learn how to describe it with limits. And so here's how we're going to do this with limits. I'm going to kind of slowly ease you into it. Let's look at the right end first. As I go to the right, if you think about my graph, as I move to the right, my x's are getting really large. So what I'm going to say is as x gets really large. And the way I do that is saying as x approaches, that's what the arrow stands for, infinity. So as x approaches infinity, or as I move to the right, my function, f of x, and remember f of x, you could think of that as saying my y values. F of x is kind of like saying y. So as I move to the right, my y's, my function, is going up. So that shouldn't be equals. As x goes towards infinity, f of x also goes towards infinity. My function is going up as I go to the right. And that's how I describe the right end. I could also say, I'm going to erase that, as x approaches, and if I want to go to the left, I'm going to say as x approaches negative infinity. And what's happening as I go to the left, as I move to the left, as I follow my graph to the left, it's going up. So I will say as x approaches negative infinity, f of x goes up towards positive infinity. So this one is the right side. This one is the left side. But that's still not considered a limit. That's just saying as x, this is just kind of a limit in disguise. The way you would write this as a limit is the right side, as x approaches infinity, f of x also approaches infinity. You would say the limit, which is LIM, the limit as x approaches infinity. So as my x's approach infinity, my function is going towards infinity. So the limit of my function as x approaches infinity is infinity. That's how you would say that right side. The left side, I want to know what's happening to my function. What is f of x doing as x goes to the left, as x goes to negative infinity, and what's happening, my function is blowing up. So that's how you would describe it as a limit. These things are called limits, the limit of f of x as x gets really big. Well, my function gets really big. Let's look at this one. What is the limit on the right end? So if I want to go to the right side, that's going to be as x goes to the right, goes towards infinity. My function, f of x, as I go to the right, my function is going up. So the limit as x approaches infinity is infinity. And that's my right side. My left side. Well, left side is as x goes to the left. So we're going to go to negative infinity. So the limit as x goes to negative infinity of f of x. Let's see, as I go to the left, what am I doing? Let's see, I am going down. So as I move to the left, my function's actually going down towards negative infinity. So that's how you describe end behavior as a limit. It's the same thing as saying left end goes down, right end goes up. That's the simple way of saying it. The math way of saying it is through using limits. So the limit as x approaches negative infinity, that same thing as saying left side, my function goes down to negative infinity. So there's how we're going to describe end behavior. It's really easy if you're looking at a graph, because you can simply see, oh, left side's going up. So as I approach negative infinity, my function goes up towards positive infinity. What makes it a little bit more difficult is when you do not have an equation. So let's just say I gave you an example, y equals 7x to the fifth minus 2x squared plus 8. And I wanted you to describe the end behavior of this, but you're not looking at a graph. And by the way, this is what a polynomial is. I threw that word out there earlier, and you've heard it before. But a polynomial is just a real simple, all you're doing is adding and subtracting nice terms. 7x to the fifth minus 2x squared plus 8. If you look at these two equations over here, it was x squared plus x. Even though that's an ugly number, we're still just adding nice clean things here. X cubed minus 4x plus 2. Real nice clean equation. That's a polynomial. So what we're doing with polynomials, you need to know the degree. Remember, degree is found by the highest exponent. So here, my degree is 5. And the leading coefficient, whoop, I was trying to circle that, kind of failed. There we go. Leading coefficient, in this case, is 7. And what we're concerned with is whether the degree is even or odd, and the leading coefficient is positive or negative. And if we look at this case right here, this is an a positive leading coefficient, it was 7, with an odd degree. So if you have a positive leading coefficient and an odd degree, what's going to happen with those graphs is the left end is going to be pointing down and the right end is going to be pointing up. And there could be some goofy stuff going on in the middle. I don't care. All I care about is the ends. If you have an even degree, then even degrees both point in the same direction. If it's a positive coefficient, then both ends will point up. If it's even with a negative coefficient, they both will point down. And if it's an odd degree, that means the ends will point in different directions. With a negative coefficient, left end will go up, right end will go down. So those are the four cases, and it's all based on the leading coefficient, whether it's positive or negative, which is then, and the degree, whether the degree is even or odd. So here I have a couple of polynomials, and let's look at this one. We have an odd degree, which means they're going to go in different directions with a positive leading coefficient, and odd degree positive leading coefficient means the right end is going to go up and my left end is going down. Let's describe that with limits. So let's describe the right end with limits. That would be the limit as x. If I'm going to the right, x is going to infinity. So the limit of my function, as I go to the right, my function is going up. So we're going to positive infinity. As I go to the left, I would say the limit as x goes to negative infinity. So the limit of my function, as I go to the left, which is negative infinity, my function is going down. So I go left and down. So down means the limit is going towards negative infinity. And that's how you would write it in terms of limit. I expect us to have a really hard time with limits right now because that's something completely new. You've probably never seen that before. Let's see, number the next one down here. I haven't numbered any of these. What's the degree of this one? Degree is your highest exponent. Ooh, I put the degree on the right side this time. So my degree is even. And my leading coefficient, you got to watch the sign. My leading coefficient is negative. So an even degree means both ends will point in the same direction. An even degree with a negative coefficient means both ends will point down. So I know this one is going to look like this. In the world of limits, this thing is going to be for the right side. The limit as x, if I'm going to the right, x is getting large, I'm going to the right, so moving towards infinity. The limit of my function, and where's it going? See, as I go to the right, my function is going down, so that would be negative infinity. My left side is as x goes to negative infinity of my function. And as I go to the left, my function is going down also. So both ends are going down. So we're approaching negative infinity as I go to the right and as I go to the left. So there's end behavior. It's dependent on the degree and whether or not the leading coefficient is positive or negative. And we're going to try to describe it with limits. I'll be a little bit flexible for this first bit, but after a while I'm going to want you to be able to do it with limits without any trouble. Moving on, the next part, the intermediate value theorem. This is much easier, although it sounds kind of tricky. The intermediate value theorem, the most common application is to prove that the function has x-intercepts. And here's essentially what the intermediate value theorem says. 3 years ago, I had a little girl. So here's my little girl. And when she was born, she weighed, we'll just say 7 pounds. There were some ounces in there, but we'll just be real simple. Pounds. Let's not abbreviate pounds. There we go. So 7 pounds. That's when she was born. Okay, right now, she is 3. Actually, she turns 3 in a couple of weeks, but we'll say she's 3 right now. 3 years. Right now, she is grown. She is this big now. And she weighs about, we'll say 30 pounds, somewhere in that vicinity. So I started here and I grew to, or she grew to 30 pounds. The intermediate value theorem, what that says, and this is going to be kind of a stupid statement, but what the intermediate value theorem says is sometime between when she was born and she turned 3 years old, sometime in that time frame, she weighed 20 pounds or 21. It just proves that I hit every number between 7 and 30. So yeah, obviously she had to weigh 20 pounds at one point because we went from 7 to 30. She weighed 25 pounds at one point. Since 25 is in the middle, is somewhere between 7 and 30, intermediate, that's where the intermediate comes from, somewhere between 7 and 30, I had to hit every single number. And that's what the intermediate value theorem says. If I go from 0 to 12, I have to cross 11 somewhere. The way we prove roots is by having a real function, and here's what I'm going to do here, show that the following polynomials have roots, and remember roots are also x-intercepts. And the way we're going to do that is we're going to plug in these numbers. Now this is an interval, that's not an ordered pair. This is an x-coordinate, and that's an x-coordinate. So what I'm saying is I'm going from x equals 2 to x equals 0 to x equals 2. So what I'll do is I'm going to plug those in. I'm going to find f of 0. Let's plug in 0. 0 squared is 0, minus 6 times 0, minus 7, and I get negative 7. So at 0, I was at negative 7. And at 2, 2 squared is 4, and this is not going to work, is it? This is what you call a bad problem. How about we change this to, this is a bad problem, isn't it? Let's change that to plus 6x. There we go. My bad. Starting over, x squared plus 6x. So that's going to change that to 0 plus 0, which is still negative 7. Sorry about that. Okay, so x squared plus 6x minus 7. Then if I plug in 2, I get 2 squared is 4, plus 6 times 2 is 12. Minus 7. 4 plus 12 is 16. Minus 7 is 9. So what I did is when I plugged in 0 for x, I got negative 7. So I'm down at negative 7 when I plugged in 0 for x. Then when I plugged in 2 for x, I was up here at 9. So my y-coordinate was 9 when I plugged in 2. Well, if I go from negative 7 to 9, I changed from a negative number to a positive number. If I connect these 2 points, it doesn't matter how I connect them. I could even like go down and then come back up. If I connect those 2 points, I have to hit my x-axis somewhere. since I went from a negative value to a positive value, I have to have an x-intercept somewhere on that interval. Now, we're not saying where it happens. I don't know where it occurs. I just know that it does happen. Just like with my daughter, since she went from 7 to 30, I know at some point she had to weigh 20 pounds. If I go from a negative to a positive, at some point I have to cross 0. And so let's do it with this one. F of x equals this one, equals all that stuff. So let's plug in negative 2. We're going from negative 2 to 2. So negative 2, that'd be negative 2 squared minus 2. Negative 2 squared is 4, minus 2 is 2. Okay, well, let's plug in positive 2. Let's see, 2 squared is 4, minus 2 is 2. That's weird. Okay, so what happened on this one? I plugged in negative 2, and I got positive 2. I plugged in positive 2, and I got a y-coordinate of positive 2. So I'm going from here to here. Do I have an x-intercept? You may be thinking no, but it's possible. I might have an x-intercept. So what I'm going to do, just to see, because right now I could connect these very easily without having an x-intercept, right? But I could also come down and come back up. Hey, look, I accidentally drew lips. How cool is that? I could come down. So it's possible I have x-intercepts, but I just don't know it yet. What I need to do is I really need to have a sign change. Right here I went from negative 7 to positive 9. I really need to go for a negative number. So let's plug in some other numbers. Let's plug in f of, let's try negative 1. What happens if I plug in negative 1? See, negative 1 squared is positive 1, minus 2 is negative 1. Aha, look at that. So if I plug in negative 1 for x, now I'm down here at negative 1 for y. And now I know I have to have a root, because from negative 2 to negative 1, my y-coordinate went from positive to negative. I have to have a y-intercept, or an x-intercept. So now that I've changed signs, now that I've gone from a positive value to a negative value, I know I have an x-intercept. And that's what we're trying to do here, show that we have x-intercepts. And let's keep on going. Let's say I plugged in 0, f of 0. 0 squared minus 2 is going to be negative 2. So f of 0 is negative 2. And we could keep plugging in more. And that's actually what we're going to need to do on this problem. This is the last one. How much time have I spent? Jeez, I got to find a way to make these shorter. All right, last one. Let's plug in negative 4. And we're going to be allowed to use a calculator on this. So I don't want you to miss this because of arithmetic. Negative 4 cubed is negative 64. 4 times 4 is 16, but that'd be plus 16 plus 2. That's going to give me a, let's see, holy cow, negative 46. Okay, that's a big negative number. If I plug in 4, now I'm going to leave some space, because what I'll probably end up doing is plugging in every number between negative 4 and 4. If I plug in positive 4, that gives me positive 64. Minus 16 plus 2. 64 minus 16 is 48, plus 2 is 50. So I went from negative 46 to positive 50. Well, that's a change in sign, so I have to have an x-intercept. I changed my sign somewhere. But do we have one x-intercept? If I went, see, I was at negative 4, and I'm way down here at negative 46, and at positive 4, I was way up here at 50. So I know I have at least one x-intercept. If I connect them with the line, I have one x-intercept. But what happens if my graph does this? What if it goes up and comes down and goes up and comes down and goes up and does stuff like that? We could have a whole bunch of x-intercepts. So I'm going to see if I could find any more. I found one. Let's see if there's more. And to do that, we're going to plug in every number between negative 4 and positive 4. F of negative 2. F of negative 1, f of 1, f of 2. That's supposed to be an f. What am I doing? And f of 3. And we'll plug these in. And we'll see how many roots we can uncover. Negative 3 squared is negative 27, plus 4 times 3 is 12, plus 2. Negative 27, that'd be negative 13. I didn't change signs, so no root there. 2 cubed is 8, so that'd be negative. Minus 4 times negative 2 is plus 8, plus 2. That's positive 2. I changed signs. There's a root. I have to have an x-intercept because my y's went from a negative to a positive. Okay, let's keep going. Isn't this fun? Negative 1. Negative 4 times negative 1, that'd be plus 4, plus 2. That would be 5. No root. Went from positive 2 to 5. No roots. Plug in positive 1. Hey, I skipped 0. Let's plug in 0. That was stupid of me. 0 cubed minus 4 times 0 plus 2 is 2. Still no roots. Plug in 1. 1 cubed minus 4 times 1 plus 2 is 1 minus 4 is negative 3 plus 2 is negative 1. I changed signs. There's a root. Plug in 2. 2 cubed is 8. Minus 4 times 2 is 8. Plus 2 is positive 2. Negative 2, or negative 1 to positive 2. There's another root. We're finding all these x-intercepts. Anytime your answer changes signs, you have an x-intercept. And then 3 is 27. 4 times 3 is 12. Plus 2, 27 minus 12 is 15. Plus 2 is 17. So that's positive. Didn't change signs, didn't change signs. So actually we ended up having 3 roots. And that was proven by the intermediate value theorem. If you go from a negative to a positive, you have to hit 0 somewhere en route. And that's the intermediate value theorem, and now I'm done.